Hey folks, this is Charles Von Zagen here. Obviously, classes have been canceled. We have a snow day today, and campus is closed. So I don't think we want to get any further behind. So I'm recording a few lectures to cover. First of all, I'd like to go ahead and cover the topic of 3.11, which is on the subject of related rates. And so we'll work through some videos of this, and then you can get started on the homework. To be honest, this is actually not a bad topic to be missing because it is just a series of applications and story problems. So we say, here's the story problem. This is how we use calculus to tackle it. Let's read through this question real quick. We're told that each side of a square is increasing at a rate of 6 centimeters per second. So the sides are increasing at that rate. So we're asked the question then, at what rate is the area of the square increasing? Okay. So this is what's called a related rates question. That is, we know that somehow the side of a square is tied to the idea of the area of the square. And we know how the side of the square is changing. We're given the rate that it's changing at. And we're asked the question, well then, at what rate is the area of the square changing? Okay. First thing I would encourage you to make sure that you recognize is every time in this class from here on out that you see the word rate, you should know that we're talking about a derivative. Okay? So if, let's just say, S measures the length of the side, then S prime measures how quickly that side is changing. Similarly, if we were to let A represent the area of the square, then the rate at which the area is changing is called A prime. So one more time, I encourage you to, whenever you see this word rate, to think of a derivative. Okay? So the typical strategies for these problems involve finding a formula that relates the two or sometimes multiple variables given in this problem together. For these first three questions that I'm going to do in this first lecture here, those formulas will all just be geometric formulas. In reality, coming up with a formula that relates two unknown quantities together can be challenging, and that'll be what the latter problems look like. So, our general strategy is this. First, we want to find a formula relating the quantities. The next thing we want to do is we want to implicitly differentiate both sides. And then we can solve for the unknown rate. And at this point we can, we've either already answered the question or we've still got just a little bit more work to do when we answer the question. So this is our general strategy. These steps, I feel like, are sort of vague, and that's because each one of these problems has its own unique qualities, and it's hard to come up with steps that encapsulate all of them. So let's go ahead and give this one a shot. Let's read the problem one more time. The sides of the square are increasing at a rate of 6 centimeters per second. So how fast is the area of this square increasing? So our first step, we say, let's find a formula that relates these quantities. Okay. Well, I think the formula that would relate these quantities is that the area of a square is equal to the side of the square squared. Okay. Now what do we do? Well, in this case, coming up with that formula wasn't too difficult, and now we move on to the next step, and we want to implicitly differentiate both sides. Let me ask this question. What variable are we going to differentiate with respect to? Are we going to look at dA dx, or dA dy, or dA ds? Okay. Well, the hint comes in the description of the rate here. Notice we're told that this is changing at a rate of 6 centimeters per what? Per second. So our implicit variable here is time. The area is a function of time. the length of the side is a function of time, and as time progresses, we're interested in how the area changes and how the sides change. So we're going to implicitly differentiate both sides with respect to the variable t for time. Okay. So this gives us, on the right-hand side, it just gives us a prime is equal to, and on the, I think I said right-hand side, I meant to say left, and then on the right-hand side we get 2s times s prime. Okay, that was through that process of implicit differentiation. Let's just go ahead and say, so I wrote that, there's nothing wrong with that, but let's just emphasize that this is with respect to time, so let's go ahead and say that's dA dt is equal to 2s times ds dt. Okay. You might find it helpful to use the Leibniz notation on these problems. So in this case, what are we trying to find? Well, the question says at what rate is the area of the square increasing? So we want to know what dA dt is. Well, luckily we do know that. Okay. So let's plug in what we already know into this equation. I don't know what the current length of the side of the square is, but I do know that ds dt is unchanging, and it is 6 centimeters per second. That is our ds dt. It's the rate at which the side of the square is changing. Well, what we don't know is what the actual side of the square length is at this point in time. We don't know what point in time we're talking about. Well, here we're told, though, that the area of the square is 16. So if the area of the square equals 16, then side squared equals 16, or s is equal to plus or minus 4, but we just take 4 for the length, because the length of the side has to be a real value. So that's what we'll plug in to our side. Okay. So we have that this is 4, and so we get that dA dt is equal to 2 times 4 times 6, or 48 watts. Well, this is a change in area. Area is measured in centimeters squared per unit time per second. So this is how quickly the area of this square is changing at this unit time. I'm going to go ahead, I'll work 2 more examples, but I'll go ahead and pause this video now so I can upload it for you.